Session 12, Eigenvalues and Eigenvectors of a square matrix, Cayley Hamilton theorem. Statement and its proof. Let us consider a square matrix A be an n-row square matrix and lambda intermediate. Then the matrix A minus lambda I is called the characteristic matrix of A, where I is the unit matrix of order n. Then the determinant of A minus lambda I can be written in this general format like this, which is a polynomial in lambda of degree n is called the characteristic polynomial of A. Then the equation A minus lambda is equal to 0 is called the characteristic equation of A. This is the characteristic equation, and the roots of the roots of this equation are called the characteristic roots or characteristic values or eigenvalues. So lambda is the eigenvalue that we need to find out here. Now next, coming to the definition of the eigenvector, where lambda is the characteristic root or the eigenvalue of matrix A, then determinant of A minus lambda is equal to 0 and the matrix A minus lambda I is singular. Therefore, there exists a non-zero matrix X, which is the eigenvector that we are going to find out, such that A minus lambda I of X is 0 or Ax is equal to lambda X is the eigenvector of the matrix A. So now in this we understood the definition of eigenvalues and other eigenvectors. Now let us solve a problem. Find the eigenvalues and eigenvectors of the matrix square matrix with the elements 5, 4, 1, 2. The characteristic equation of A can be written as A minus lambda I is equal to 0 as determinant of 5 minus lambda 4, 1, 2 minus lambda determinant is equal to 0. Now finding the value, cross multiplying the elements and the negative of this, we expansion and we are going to get the equation like this, the quadratic form. Now we are going to find the value for the lambda, and I'm going to get the value of lambda as 1, 6, which is the eigenvalue. So eigenvalue is 1 and 6. Now to find the eigenvector, case 1 we are going to consider when lambda is 6. Then the eigenvector x is x1, x2 that I need to find out for the matrix A corresponding to the eigenvalue 6 are given by the non-zero solutions of the equation A minus 6i into x is equal to 0. So what is the matrix A that we have already written there? A minus lambda, that is 5 minus lambda 4, 1, 2 minus lambda into x1, x2, the eigenvectors is equal to 0, 0. So when lambda is 6, substituting for lambda is 6, I am going to get the equation as follows. Now the equation is minus x1 plus 4x2 is equal to 0, x1 minus 4x2 is equal to 0. Both the equation gets reduced to x1 minus 4x2 is 0 or x1 is equal to 4x2. I am choosing x2 is equal to k arbitrarily, then x1 is 4k. The eigenvector x1 is given as 4k and k. This is the eigenvector that we got corresponding to the eigenvalue lambda is equal to 6. Now in the case 2, I need to find out when lambda is equal to 1, what happens. Substituting for in the equation when lambda is equal to 1, I am going to arrive at this equation of the matrices. So that is 4x1 plus 4x2 is 0, 1x1 plus x2 is equal to 0. Both these equations get reduced to x1 plus x2 is 0, where x1 is equal to minus of x2. Now as choosing x2 arbitrarily as k, I am going to result in x1 is equal to minus k because I am going to substitute in this equation. So what is the eigenvector x2? x2 I am getting as minus k, and k is the eigenvector corresponding to the eigenvalue lambda is equal to 1. So we solved here the problem for eigenvalues. Now coming to the Cayley Hamilton theorem, let's first understand the statement and go to the application part of the Cayley Hamilton theorem. Statement tells that every square matrix satisfies its characteristic equation. So now let us understand by solving a problem of Cayley Hamilton theorem where the matrix A is as usual we have solved in the previous sessions. The characteristic equation of A is given by determinant of this is 0. So we have written the characteristic equation and we are going to solve this determinant when we are at this solution, and replacing lambda by A we are going to get equation 1. Now find out the value for A. A already we know, find outing for A square and A cube, and substituting in equation 1 we arrive at the equation. See, substituting for all of these, I am going to get the final answer as 0, 0, 0, and hence Cayley Hamilton theorem is proved. So thank you.